research scholars, and dear participants. As educators and researchers in today's rapidly evolving landscape, we are constantly seeking ways to enhance our skills and adapt to new technologies. One area that is more critical and challenging than ever is applications of AI-enabled techniques for Alzheimer's disease. Understanding this is not just an advantage, it's a necessity for shaping the next generation of students and driving institutional excellence. We are incredibly fortunate today to have a true expert in this domain joining us. Without further ado, it is my distinct pleasure to introduce our esteemed guest, Dr. Joyita Datta. He is currently associated as professor in the Department of Biomedical Engineering, University of Massachusetts Amherst. She pursued her BTech in Electronics and Electrical Communication Engineering from IIT Kharagpur and post that did her MS and PhD in Electrical Engineering from University of Southern California. Our speaker has spent over 18 years at the forefront of this field, advising numerous institutions on best practices and innovative approaches. Her insights have been instrumental in bridging the gap between traditional pedagogy and the digital era. She has received many awards and accolades for her remarkable contributions in research and pedagogy. So please join me in giving a warm and appreciative welcome to Dr. Joyita Datta. Thank you so much, ma'am, for giving me time to introduce you. And the virtual platform is all yours now, ma'am.
Thank you so much for the kind introduction, Dr. Sahasarkar. I'm going to get started. Let me see. I hope you can see my screen now. I went to full screen mode. I will talk about some of our research on using AI for Alzheimer's disease diagnosis, staging, prognosis, sort of trying to tackle the disease from many different angles. So roughly, this is a summary of different things my lab does. So as was shared in the introduction on my bio, I'm an electrical engineer by training. So in terms of the methodologies, my core interests are in AI and in signal processing. And we work with different types of data, all biomedical. So for instance, we work with imaging data. So we work with primarily with PET images. PET is positron emission tomography. And then we also work with some MRI. And then we also create maps of the connectivity within the brain in different forms. And these, from a data perspective, can be represented as graphs. And on the third area that we largely work on is essentially time series data sets. So these are not images or graphs. They are essentially one-dimensional entities that we derive from different types of devices, primarily electrophysiological data like ECG, EEG, and then, but these can be, besides conventional ways to measure these in a sort of clinical lab setting, we also look at different variables to extract all of these electrophysiological time series data sets. So that's kind of like an overview of different things we cover. The focus of today's talk in terms of the main application is Alzheimer's disease. So AD is the most common cause of dementia, and the numbers of people affected by dementia worldwide are rather staggering. It's expected to be about 30 million people. It's about 30 million people now, and it's expected to triple by 2050. Now, in terms of the pathologies, the pathological hallmarks of Alzheimer's disease, the two key issues are the buildup or aggregation of these abnormal proteins of two kinds. One is amyloid beta, so which essentially aggregates in the form of plaques in the brain. This is what the plaques look like. The plaques are largely extracellular, so they build up outside of the neurons. And then the other pathology consists of neurofibrillary tau tangles. Tau is yet another kind of an abnormal protein aggregate, and these tend to tangle up within the neuron, so they're largely intracellular. And then in the course of time, as these pathologies aggregate, the net effect is that the healthy brain eventually undergoes a lot of atrophy. And so this is what an atrophied brain would look like, where the overall cortical volume would reduce, and then you would see a lot of these spaces. And so the ventricles, or the gaps in the, or these sort of empty spaces filled with fluid, they expand over time, and the cortical matter reduces. So this is kind of like a net effect as the disease progresses. Now, one of the important goals in Alzheimer's disease is to detect it early. The reason being, a lot of the drugs that are currently under development, some are approved, a lot of them are still under investigation. The general consensus in the drug development area for Alzheimer's disease is that many drugs can be promising if they're administered early before any memory complaints or actual clinical changes surface. So that means we need to detect the disease in its early or preclinical stage. So that's preclinical. Alzheimer's disease usually refers to pre-symptomatic or very early AD. And this stage can be only detected by sensing amyloid beta plaques and tau tangles from using different methods. So in other words, you cannot just give a cognitive test, some sort of neuropsychological test, to detect Alzheimer's disease in this very early stage, because it's kind of a latent stage where there are changes that have happened in the brain in terms of aggregation of A beta and tau, but these are not detectable by checking somebody's memory, if they have memory complaints or other complaints. So in this early stage, how can we detect amyloid and tau and essentially figure out that, well, this is preclinical AD and the disease needs to be sort of modified or halted before things go south. And so there are different ways to look up amyloid and tau biomarkers. And so that includes imaging. More recently, we are also able to sensitively measure certain blood-based biomarkers. So take blood samples and look up different forms of amyloid beta or tau in the blood. There's also another third way, which is taking CSF or cerebrospinal fluid samples. They tend to be somewhat more invasive, like moderate, sort of semi-invasive. And again, so overall, there are these three ways. So I'm going to talk about the imaging aspect first. So for imaging, one of the most successful ways to look at beta amyloid and tau is using positron emission tomography, or PET. So let me spend a few words talking about what PET is. So PET is an imaging modality. So it's a 3D imaging modality. You get a 3D map of the body or the brain, whatever your target is. You start off by using radio tracers. So these are radioactive agents. So the way the radio tracers are formed is you use some sort of a targeting molecule. So these molecule selectively localizes and binds to some sort of target in the body. So, so that's sort of the chemistry angle. So if there's affinity towards certain targets in the brain or the rest of the body. But that's not enough to generate contrast for us to view this molecule that is attached to a radioisotope. So this is a positron emitter. And when you create, the net effect of this is a targeted radioactive agent. And so you inject that to the body and you put the person inside of a scanner, and then you collect data, you reconstruct using a physical model and a statistical model. And after image reconstruction, you end up with this 3D volume that tells you that essentially maps all the positron emitters that have localized in different regions, giving you a 3D image. So that's the idea of PET. Now, in Alzheimer's disease, there are multiple PET tracers. So again, depending on what agent you use, such as these names given in brackets here, you're going to see something very different, because each of these agents have a different targeting molecule. For PET, again, there are certain positron emitting radioisotopes that you can use, most commonly F18 or C11. So you attach that to this chemical entity that selectively targets something in the body. So the most common ways to use PET in AD, number one, is to target glucose metabolism, to try to throw in analogs of glucose in the body. So 4-deoxyglucose, for some part of the respiratory cycles, kind of mimics glucose. So it enters the respiratory, sort of the respiratory process, the glycolytic phase, and then it at some point it cannot pursue the full chain, but because it enters that cycle, it actually is very useful as a visualization tool in cells that undergo a high rate of respiration. Usually these are, for instance, in cancer, FDG is widely used in cancer because cells that are cancer cells tend to have very high metabolism, so they consume a lot of glucose naturally. And so instead, if you use a glucose analog, it's going to show up bright in those cells. Similarly, in the brain, what happens is, we talked about atrophy. So when there is atrophy, then the locally in regions that undergo atrophy, the cells actually metabolize less. So there's hypometabolism. So FDG is quite useful as a biomarker for neurodegeneration. And so, that's one way to look at any neurological disorder. If there is like a neurodegenerative angle, that's that can also be mapped using FDG. On the other hand, we spoke about amyloid and tau. These are more direct markers of Alzheimer's disease. One of the great things that happened in the Alzheimer's imaging world was about 20 years back or so. The first compound for mapping amyloid in the brains of live individuals was first invented in the University of Pittsburgh, so it came to be called Pittsburgh Compound B. And so for the first time, we could actually look at amyloid in living individuals. Before that, the only way to definitively say this person's brain has amyloid was via autopsy. After somebody has died, chopping their brains up, looking at slices under the microscope. So being able to look at amyloid in the brain was quite revolutionary in the Alzheimer's imaging field. And so soon after this initial compound, there were several F18 compounds that were invented. And this was important because F18, as this radioactive entity, has a longer half-life, so you can you get much more you get better signal when you're imaging it over a period of time. So that's amyloid. So there are multiple different amyloid tracers that are currently available for amyloid. The tau, on the other hand, initially was thought to be, well, maybe amyloid, once we get amyloid imaging agents, this is going to give us all the tools we need to conquer AD. But soon it turned out that once we started looking at amyloid in the brain of live individuals, what we realized was that amyloid aggregation, although it was a critical aspect of AD, it was not directly related to the actual cognitive decline and the endpoints in AD. So that was quite a puzzling discovery. And in fact, tau has been traditionally associated with having a very direct connection with disease progression in AD. And so the next target in the imaging world was to discover imaging agents for tau. And so the first one of those was fluortazapir, which is still kind of standing strong in the AD neuroimaging field, but then there have been other agents. So that's sort of my little background on Alzheimer's disease. I just wanted to sum up by saying, in terms of characterizing this disease, one of the most handy frameworks right now is called the ATN framework. So we look at amyloid, tau, and neurodegeneration. And PET is quite useful here because we have tracers for all three. So, and again, the focus of my talk is going to be AI, so I'm going to switch gears very soon. But roughly, these are the 4 questions that I'm trying to answer today. One is, how can we create better images for Alzheimer's disease? How can we forecast the spread of tau? I mentioned that tau is very directly correlated with disease progression. So then the question is, is there a way we can forecast how tau will spread and across the brain and contribute to disease progression? The next question is, how can we stage Alzheimer's disease accurately? As this disease is advancing, how can we assess how advanced it is in a data-driven manner? And lastly, these 3 topics are very imaging focused, and then we'll switch gears and talk a little bit more about other modalities and try to answer the question, how can we detect Alzheimer's disease early? So with that, I'll start talking about image enhancement using PET. So quantitatively speaking, when you're trying to quantify biomarkers with PET, there are 2 big challenges. One is low spatial resolution, which is due to a number of factors, including both hardware factors like scanner parameters and software parameters, including how you reconstruct an image. On the other hand, there's also a lot of challenges in PET quantitation due to high noise in the images. And there is a lot of motivation to suppress noise. For instance, if you want a shorter scan, usually shorter scans, faster acquisition is associated with higher noise because you get fewer counts, fewer photons are detected in the course of that shorter time frame. And so if you have good noise suppression techniques, you can reduce scan time. You can also reduce tracer dose. So you inject radioactive agents, you can get away with injecting less of radioactive agents, which is, and of course, as you know, any kind of radioactive agent is deleterious for your health and because due to radiation damage. And so there's motivation to reduce radiation dose. So for these reasons, there is strong motivation to denoise images, PET images, and also de-blur PET images. So these are two problems I'll be talking about. One is trying to improve the resolution of the images. In other words, to de-blur them. And the other one, and the other goal is to reduce the noise in images or denoise them. So in both cases, the goal is to train some sort of neural network that would map either the corrupt image, either a blurry image or a noisy image, to the target clean image. So that's the general goal. So what are neural networks? So I'm going to start from basics, assuming I understand several of you may know this stuff already, but I wanted to give a very brief background. When we talk about AI nowadays, most of the modern AI techniques, compared to some of the more classical machine learning techniques, are based on what's called deep learning. So deep learning involves creation of deep neural networks. So these are networks that start with a set of inputs, compute features sequentially by passing these features through layers. And so you have a set of features there, use them to compute a set of derivative features. Here, the first set, through this first layer, they're passed through some nonlinearities to make sure you're not simply just creating a linear combination of these inputs. And this nonlinearity adds extra complexity and improve the model capacity. And then once we create the first layer of features, we pass them through another layer of, again, linear combinations and activations. The result of it is a modified set of features that are functions of the first set of features. So as you go from layer to layer, you can see there are these interconnections. So every unit of every layer is getting information from every unit in the previous layer. So the features are getting sequentially passed and combinations of features are being created. So that essentially gives it the ability to learn very complicated information by just passing the information down through a multitude of layers. And finally, we create a set of outputs. And the inputs and output depend on the problem at hand. You're usually starting with some input and trying to predict something. And this could be either in the case of imaging, maybe you're trying to create an image. Maybe you're trying to make a decision, a clinical decision, such as diseased or not diseased from an image. So depending on that, your input and output would change. You normally give some sort of constraint to create a loss function that would help train this network. So you would learn the parameters associated with each of these layers. Once you have learned all the parameters, then you would essentially deploy that network, and now I can just directly apply it to predict outputs for certain inputs. So that's a very basic concept. So there are all kinds of neural networks that are used. What I just described to you is a so-called fully connected neural network where every unit in one layer is connected to every unit in the next layer. So in these setups, you have lots and lots of connections. So associated with every connection, there's a weight which you need to learn while training the network. So this is a fully connected neural networks example. So you go, if you have this 4x4 structure in this example where you go from 16 pixels, 4 times 4, so this is a 16 by 1 vector, to a 4 cross 1 vector. You're just trying to compress the size to get to this final decision of, well, is this a cat or not a cat? So now if you connect, if you count all the connections, you'll see that between these two sets of layers, you would end up with 73 connections. Now for data that lies on a grid structure, like an image, everything is laid out on a grid. And so every pixel has a few other pixels that are its nearest neighbors. And so For these grid structures data, a particular type of neural network that is very, very efficient and convenient to use is a convolutional neural network. These convolutional networks, they rely on the idea of convolution, which is a local operation. So they extract information from a local set of features. So if I'm looking at this pixel, then I'm only going to explore its relation with its most immediate neighbors. So you can see here how these are essentially, we look at connections between only the nearest neighbors of its pixel. And so compared to this, you see here that you have way fewer connections. I'm not looking for information that connects this pixel with this very far away pixel. So we only focus on nearest neighbors. And so in this setting, the total number of unknowns is drastically reduced. And that's what makes convolutional neural networks very, very efficient for grid structured data like images. And then farther down, one of the very robust networks that have come to be is the so-called generative adversarial network. So the basic idea of, again, is very interesting. So you have a generator network that produces some sort of an image, and you create, and that's not your only neural network, you have two competing neural networks, a generator and a discriminator. The generator tries to create realistic images, and the discriminator takes this generated sort of the synthetic image, which we call a fake image because it's created by a neural network, and it compares that fake image with an actual true image and tries to decide whether this is real or fake. So now, depending on how realistic this looks, the discriminator could be right or wrong. And the way GANs work is that these two networks are trained together in unison, which means as you kind of iterate and try to compute different weights for these associated with these networks over time, the generator becomes increasingly better at creating realistic images, and the discriminator becomes increasingly better at catching fakes. And so when you train them together, eventually you'll have a network that is capable of creating very, very, very realistic images. And so GANs have developed a reputation for being very stable and robust, if you can train them well, that is. Because you can think of them as, let's say you create a CNN as a generator to create an image, but here you have kind of an extra layer as a sanity check to kind of self-check the image quality before you provide the output. So that's kind of the concept. And then in more recent years, transformers have really led to a paradigm shift in the AI field. So everybody, I assume, is familiar with ChatGPT. So in GPT, the T stands for transformer. Originally, transformers were proposed for the natural language processing, or NLP, domain. But in the current setup, we've seen the emergence of so-called vision transformers, the same concept being extended to images. And transformers rely on this concept called attention or self-attention, which essentially enables us to kind of look at global similarities in a dynamic way in the data provided to you. And the couple of comments very briefly. So because they look at global similarities, they can be much more powerful than CNNs, which are largely local. That being said, they rely on a lot of data. So in other words, in order to train a transformer well and to get it to work at its very best, you need very large volumes of data. So they can be expensive to work with. And so in terms of the methodological literature in medical imaging in general, we've seen sort of a bit of an evolution here, starting with like shallow to deeper CNNs, to UNet, which is kind of like a convolutional network variant, to GANs, to transformers. And most recently, we've seen the emergence of so-called diffusion models. And so I'll talk a little bit about those later in my talk. But the other thing that has happened is in the initial years, we found like all networks were pretty much fully supervised, which means when we train these networks, we provide inputs and corresponding sort of one-to-one matched outputs. So that means before we can train a network, we have to very carefully label the data. So if we are trying to identify cats from images, then our data has to be accurately manually curated to label each sample as cat or not cat. The same applies to medical applications. Everything needs to be there has to be a known output for every input in your training data. So over time, there's been a lot of interest in coming up with unsupervised, weakly supervised, and self-supervised formats where you have less of a need for manual labeling of data. And so again, the fully supervised setups continue to be used today, but we have many more options to do unsupervised learning. So the first topic I'll cover is super resolution PET. And in the context of, I was talking just now about the requirement for paired labeled data sets. So again, in a very simplistic setup, you will train the network using a set of low resolution images. These are blurry images. And for each of them, you will have a high resolution counterpart. So you have LR and HR data sets where everything is nicely matched. So I have this image, which is blurry, and I have its counterpart, which is the sharp version of that exact same image. So this would be a paired training data set for super resolution network training. But in reality, what often happens is we may have low resolution images from an imaging scanner that is old and produces very blurry images. The technology is not as advanced. On the other hand, we may have high resolution images from the latest and best imaging scanners that produce the 3D images, such as PET images or MR images. But then we may have, but most likely these high resolution images will be from a different cohort. It rarely happens that the same person is imaged in two scanners. And again, for AI model training, you need very large data sets. And so you kind of dig into existing data banks that a hospital or some society may have curated. So again, it matched training data sets from two different scanners would be relatively rare. And so a more practical scenario would involve using unpaired images for training. So some of our old work in this field was using very deep convolutional neural networks for super resolution. And our first paper on this topic was actually a paired sort of a supervised framework that's based on paired training data. And so we used this, developed this network architecture that was very deep, but in addition to just having a convolutional backbone, some of the key changes we incorporated was the introduction of anatomical information. Typically, PET scanners give us functional information, such as some of the examples I mentioned about, glucose metabolism, amyloid, tau. These are all functional variables. On the other hand, modalities like MRI, especially structural MRI and CT, tell us about structure or anatomy, like where is the gray matter versus the white matter, or where is bone versus where is air spaces in the lungs. So these are things that MR or CT images would be good at telling us. And so the anatomical modalities tend to have much higher resolution than functional modalities in general. And so having some anatomical guidance from an MR image could actually help enhance the resolution of a PET image. And in addition, one of the interesting things about PET is that the resolution is not fixed. It varies depending on where in the body you're looking. So it's on this radial and axial position in the scanner. It also varies depending on the intensity. So this initial idea that we had for building a super resolution imaging architecture for PET, it included these other inputs that includes spatial information and anatomical information. And again, I don't want to go into into deeper details of this, but very briefly, we compared it with existing analytic methods to go from low resolution to high resolution. And we also compared shallow architectures, S1, S2, S3, S4, shown here, versus V1, V2, V3, V4, which are the very deep. And here, 1, 2, 3, 4 refers to the number of inputs. And so we showed that with all these 4 inputs and a very deep architecture, V4, we were able to create images that actually very nicely pick up some of these small, minute details in the images. And so this is the original low-res image. This is a target high-res image that we are trying to generate, and this is what we came up with our best network. And here's a zoomed-in version. You can see like some of the smaller details that are not picked up in these other images actually show up in this best case. Since then, we've been focusing on settings that require unsupervised training. So you have unpaired clinical data sets where you have data from one scanner, which is a low-res scanner, and data from another scanner, which is a high-res scanner. And these are unpaired, where you have different cohorts being used. And so on that front, we created the self-supervised super resolution framework, which involved a generative adversarial network, or GAN, which I told you about, where there are two sets of, where there are two networks usually, where there's with one being a generator, one being a discriminator. So this is a slightly more complicated setup where we have two sets of generators and discriminators. And the idea I can explain to you is, again, I'm going to, in the interest of time, I'm going to say very briefly what we are trying to do is we're mapping from the low-res domain to the high-res domain using a generator and then a discriminator that tries to do a quality check. Well, is this similar to a high-res image or not? So is this image realistic or not? But we go through another layer of checks. What we do is we map this high-res image back to the low-res using another generator. So this goes from low to high resolution, and then this goes back from high to low resolution. And once we go map this back to the low resolution domain, because we create a synthetic low resolution image, we can actually do a direct pixel to pixel check of the synthetic low res image with the original low res image. So the LR prime and LR. And so this gives, this is called a cycle consistency term, and it gives an extra layer of a quality check, which contributes to the robustness. And so another thing that we did here, because the mapping from low to high resolution is a very difficult problem, we also added this, from the previous network where we did supervised training, we used that as a feature extractor and added these additional simulation guided features to further enhance the network's performance. And so we did very extensive comparison, and we showed that this network that has simulation guidance ended up being the strongest performer. And these are some close-ups where you can see this is the original low-res small patch from the brain. This is the high-res image. And this is what we get with our method compared to these other methods. You can see that these smaller regions or brighter regions, you can see the enhancement in compared to all of these other reference methods where it looks like a uniform blur. And these are some quantitative metrics. I'm not going to go into the details of what these are. One of the most important ones here is the PSNR, or peak signal to noise ratio. And this is in decibels. So a difference of more than one is actually considered a sizable difference because it's in an exponential scale. Okay, so I talked about diffusion models. Diffusion or diffusion probabilistic models are actually currently a key component of all modern text-to-image generation tools. So this is kind of like a fun example. If I asked ChatGPT to recreate Mona Lisa in the style of different artists, Van Gogh, Monet, or Picasso, it actually does a pretty good job picking up all of these very unique stylistic details of each of these artists, like these swirls in Van Gogh, or the light and dark effects of Monet, or the angularity of Picasso, and so forth, which is quite remarkable. And so what are diffusion models? So diffusion models are I would say they're statistics-guided iterative models for image generation. The idea is that, and one thing to note is these are generative AI models, where if we throw in a random input, it is able to produce a sample from a distribution that it has learned. The way it does that is by by developing a mapping from a known distribution, such as the Gaussian distribution or the normal distribution, which has this plain bell curve. And this is something which is easy to sample from. We can use any random noise generator to sample from that distribution. And what the model involves is a mapping from this to the final target distribution. This is the distribution corresponding to a set of target images. And this mapping from here to here is done in iterative steps and is essentially involves kind of looking at it from two different directions. One is the diffusion process, or the forward process, where if you start with a perfect image and you gradually add noise to it, and you see how as you make it noisier, it degrades over time until we have pure noise. The entire signal is drowned in noise. So that's the diffusion process or noising process. And then there's a reverse process ultimately, which we want to learn. And this involves denoising these images, these pairs of images in the sequence where you go from here to the next less noisy one, from here to this, from here to this final image, and so forth. And this is where the learning part kicks in, because essentially what you'll learn is something like a denoising network to progressively denoise this image. And so that is a basic diffusion model. Now, in some of our practical cases, what we want to do, as I explained, was denoise or deblur. So if you start with a blurry image, end up with a deblurred image, or start with a noisy image, end up with a denoised image. So for these special cases, you also have additional inputs, information in the form of a blurry or noisy input. And so you provide that as a so-called conditional input. So this is a conditional diffusion
Dr.
model.
Datta,
Yes.
I'm sorry, ma'am, to interrupt you. Ma'am, actually, the slides are not very clear. Now, especially for the last 10 minutes, it is quite blurred.
Okay, so maybe I'll try to.
Could you please reshare once? Yeah, and just check.
Yeah, let me see. Because I'm using Teams from my browser, it's a little tricky. Is it any better?
Still the same, blurred.
Okay, I'm gonna close this window and then I'm gonna try to share again.
Yeah.
Okay.
I guess there's some internet issue at your end or anything like that, ma'am, because your video is also very blurred now.
Oh, really?
Yeah.
How about my screen? Can you see it now?
Yes, we can see the screen, but however, the blurredness is still there.
It's still there? I mean, I can see and hear you, so I'm not sure.
I understand. Yeah. All right, ma'am, no issues. You can continue. Let's see. Maybe after some time, if there is a lesser fluctuations in the internet, we will be able to see again back.
Okay, I'll try
Please
that. Sorry about
continue.
that. Yeah.
No, that's okay.
From my end, I can see and hear you, and so yeah. Okay. Continue to share. Okay, so as I was saying, so you can use a diffusion model to deblur or denoise. In the interest of time, I'm also going to move forward a little bit. So we have this somewhat sophisticated approach for using diffusion models to do the same mapping from one scanner's domain, like a low-res scanner's domain, to a high-res scanner's domain. And so we have two sets of scanners here, and this is actually for tau PET imaging. The previous example was for FDG PET imaging. Both are, again, targeting Alzheimer's disease. But the basic idea is to create a somewhat more sophisticated network where we first map the blurry image from an unknown blur domain, because you don't know exactly what the mathematical model is for the blur, to a known blur domain, which is a simple Gaussian blur. And then we use a diffusion model to learn to essentially do the mapping from the blurry to the known blur domain. So that's kind of mathematically what's going on in the background. And essentially we these are results from a clinical tau PET data set where we're going from we're essentially doing this mapping, but using completely unpaired data. We have two different cohorts from two different scanners and two different two sets of sites. And so everything is different. And so we show that with this diffusion-based paradigm, we actually get the sharpest images. So with that, I'm going to move on to a slightly different direction, which is image denoising. So if you have a set of images that are noisy and a set of images that are less noisy or noise-free, then we can develop a model to connect the two. So the first, so again, in a sort of parallel to what I was saying for the super resolution problem, you can do this using a paired approach where you have pairs of noisy and low noise images. But in a more standard clinical scenario, you have only low count or high noise images available. So this is a single noise realization of noisy images, and you're trying to figure out how to reduce the noise in them. So that's a more challenging problem. And so some of the early work that we did in this field was using these masked architectures for suppressing noise. And the essential idea here is that if you have you have a case where you only have noisy images, there are no target low noise images, you provide that to some sort of a convolutional network as an input, and you say, well, this same noisy input is identical to my output. So in that case, it kind of becomes a trivial problem where it's trying to match the input to the output with no change. So it's just going to have the prediction is going to be the same as the input because it's not going to try to denoise at all. But the paradigm changes when we say, well, I'm going to mask the central pixel in my patch, and my goal will be to learn or make the best guess for the value in this central pixel using only the information from the neighbors. And so because the central pixel is masked, I don't know its noisy value. And so when we provide this kind of a constraint where it has to learn from the neighbors, it's a much more constrained setting. And so it's forced to learn something different than the actual sort of noisy input for if you compare the value in the central pixel to the original noisy value in the central pixel, that's going to change. And so this is kind of the idea of it's called blind spot masking or just simple masking. So there are many masked architectures that kind of force networks to learn information from images in this sort of roundabout way. And so this is what we developed was this masked architecture we call noise to void. And one of the other things that we did was, well, you could do this image by image, and then you'd have to train a neural network for every single image, and that could be expensive. And not just expensive, it could be slow and unstable. And so a more stable approach is to do this at a group level. So we call it group level or population level pre-training, and then individually fine-tune the models for each for each case that comes by. And so we got interesting clinical and simulation results on this, where we show that when we provide anatomical information as guidance, and we also use this pre-training model, our network provides the best images in terms of quality and also in terms of quantitative accuracy, so that these are PSNR maps, peak signal to noise ratio maps for the images. Now, in this, for this topic too, we have recently been working with diffusion models. One thing I want to mention about diffusion models is they tend to be slow. And so that has led to the interest in a lot of different modifications of a basic diffusion model. One of them is a so-called latent diffusion model, where the idea is instead of running this very expensive diffusion process, going from iterating through different levels of noise, we instead of running that in the full size image space, we run it in a lower dimensional space. So we map it from the full size image to a lower dimensional vector, which is much more compact and efficient to work with, and then run diffusion in this lower dimensional space and then map the result back. So one of our most recent papers, which just got accepted in an IEEE journal, is based on a diffusion transformer. So again, it's a somewhat complex architecture. The main goal is to make sure that we create something very robust, which works for different PET tracers, different scanners. So it's very adaptable and works very well to data types it has not encountered before. And so it's a bit of a complicated setup here. The two main things that I want to point out is instead of using a traditional convolutional neural network as the main training, as the main learnable and teachable unit, we use a transformer, which is much more improved learning capabilities for larger data sets. And then the other thing is it uses a latent structure where we go from the full-size image to a lower dimensional space, which makes the training much more economical. And so we applied this to a pretty sizable data set across 3 different tracers, 2 different scanners. So we have FDG, which is for glucose hypometabolism, fluortaucipir, which is for tau PET, for beta-pir, which is for amyloid PET. And so we showed that compared to a wide range of alternative methods, which include diffusion models, convolutional neural networks, even pure transformers, this model actually works the best across different tracers and different scanners. These are results. 2 slides are from 2 different scanners. Both of them are Siemens models. And it's a clear winner based on a range of different evaluation metrics. And then this is a multi-view example because we are using individual slices. We just show that, yes, even when we look at it from multiple views, like, so this is, if you're looking at it from the top of the brain, this is slices from front to back, and this is like a sideways cut. All of those give relatively uniform looking images. And then this is an out-of-domain example where the scanner, where the model was applied to a data set that that is from a different tracer. So C11PIV, which is typically more noisy. And again, compared to the other methods, this was a clear winner. So I'm going to switch gears now a little bit, and I'm going to talk about forecasting tau aggregation. So tau progression, tau, again, just to remind you, these are abnormal protein aggregates that are a key characteristic of Alzheimer's disease. So tau spreads through the brain. It starts locally, and then it kind of spreads. It spreads through different regions of the brain. And tau aggregation is actually a way to stage Alzheimer's disease. So this is called Braak staging, where you go through sort of, initially you see that the tau is localized, and then in the later stages of disease, in the more advanced stages of disease, it's spread throughout the brain. And so theoretically, this is what Braak staging would look like. And this concept was built based on autopsy data. And then there's fluortaucipir, which is PET-based, and you can see how the PET imaging can recapitulate stages that we have learned through histology by looking at tissues under a microscope. And so a very interesting aspect here is that the propagation of tau is now known to be linked to the brain structural connectivity. In other words, different parts of the brain are connected by white matter tracts. So these are the axons of the long axons of the individual neurons that connect different parts of the brain to each other. And the way to map these tracts, we can't do it using PET, but we can do it macroscopically using other imaging modalities. One of the primary options available is called diffusion tensor imaging, which is actually based on MRI. And the idea is to put it very simply to get some information about how water diffuses or moves from one part of the brain to another, and essentially establishing the directionality of that movement and assuming that, well, that directionality tells us which way the tract is running in the brain. So that's kind of a very simple way to put it, but using these multiple sets of diffusion images to compute diffusion tensors, and from those tensors we extract the directionality information to extract the tracts of the brain. These are literally a bundle of tracts that we think are connecting different parts of the brain. And from here, to put it mathematically, we generate a matrix called a graph adjacency matrix that's essentially telling us how well 2 regions are connected to each other. And so now putting tau progression as posing it as a graph diffusion problem involves saying, well, this is the original distribution of tau in the brain. We have some nodes that have some amount of tau, and we know their structural connectivity from DTI. And we are trying to predict the future aggregation of tau by posing it as using this differential equation, which actually looks like the diffusion equation, if you're familiar with that, where the L here stands for the graph Laplacian, and that's like a spatial second derivative. And so this is the basic concept, but pure diffusion, unfortunately, cannot explain aggregation or increase, because if you, let's say, diffusion involves putting a drop of ink in a tumbler full of water, what's going to happen is the ink is going to spread. It's going to become uniform. But what's not going to happen is the ink, the quantity of ink in the tumbler won't increase over time. But when it comes to tau aggregation, there's spread happening, but then there's also increase happening. And so some of the work we did early in this space was to model the production of tau using source terms in this differential equation setting. So this is a graph domain differential equation. And using this, this paper that I've cited here shows a model for individual prediction, where if I know the tau at time point 1 and 2 in an individual, can I forecast the tau distribution at time point 3? So now this is an individual to individual model, and some of our recent work in this space has been to go from population level, learn how the evolution of tau happens from time point 1 to time point 2, and use that to predict tau at time point 2 from time point 1 in an individual. So you learn from a population, apply to an individual. And so this is some ongoing work in my lab. So we approach this not from an analytic differential equation perspective, but using a graph neural network model. And so we have this graph model. We also have a so-called physics-based regularizer term, so that you can think of this being some sort of a hybrid model where we are learning, but we're also using existing knowledge from physics, and that physics component, which is based on some sort of a differential or stochastic equation, and that is being applied as is being used to inform the AI model. So this is a physics-informed graph neural network model. And there are two different physics constraints we're using. One is the Fisher KPP, and the other is the epidemic spread model. And so this is our data set. We have 163 subjects in our data set. In the interest of time, I'm going to quickly move ahead. And so again, this is the concept of a graph. So we have nodes, which are regions of the brain. We have edges that connect the nodes. So these are strengths, the connectivity. And if from here we create a node feature vector, so this tells us how much tau has accumulated at each different region. And we create an adjacency matrix that tells us how strongly the regions are connected. And so depending on the strength of connection between the two regions, we expect there to be similarities or in terms of tau being sort of passed down from one region to another. And so the graph neural network, conceptually, it relies on the concept of message passing across a network where you have a set of nodes, you have some information in the nodes, which are indicated in sort of different shades of blue here. And as we sort of iterate, or as the graph goes through different states, it essentially, this information is passed from one location to the other through these connections in the nodes. And then what a graph neural network does is it passes this information, then aggregates the information across the nodes to create a new state for the graph. And so putting it all together, in our case, our GNN is in a latent space where we initially use an encoder to map the information from the initial, from the node level to create these composite vectors at each node. And then we train the GNN to do message passing. And finally, we map the information back to the original domain using a decoder. So that's the basic idea, and that this is the network layout. We have the node encoder, the GNN, the node decoder, and we apply this physics constraint here, which is captured by this component of the loss function that says lambda times LP. And we in our experiments, we used sort of different variants. So we compare different inputs. So one case is when we just use the initial tau alone. One case is when you have initial tau and amyloid, both provided as vectors. And the third one is where we have tau and amyloid, but the amyloid information is either is provided as a binary variable, either amyloid positive or amyloid negative. And then we have also different regularizer variants. So one is no regularizer, one is Fisher KPP, one is the epidemic spread model. So these are some results here where we look at errors in the in our estimation of tau. So this is when we use tau only as input. What we're showing here, these are confusion matrices that tell us whether a comparison between true and predicted results for three different for multiple cases. One is when tau is not increasing versus increasing, and we are trying to see how well we're doing when we in terms of predicting tau increase or no increase in an individual. And so between these three methods, you see different accuracies for each of these cases. And these off-diagonal terms are actually cases where we are estimating things incorrectly. So ideally in all these matrices, we want the diagonal terms to be high and the off-diagonal terms to be low. And so this is the what we get when we provide the tau vector, so tau in different regions, and amyloid vector, amyloid in different regions as inputs. So we have dual inputs here. And we see how, interestingly, the accuracies actually go down. So this is about 60 and 76. It goes to under 60 here to about 76 or 77. And so this is, even though this seems like, well, we have more information, why should it go down? But part of the reason it's kind of, there is some rationale to it, some physics rationale to it. So one of the things that, that we see in literature is that tau seems to have a very clear relationship with structural connectivity, but amyloid not so much. Amyloid seems to rely more on physical proximity in the way it spreads than structural connectivity. And so when we provide spatially varying amyloid as an input to the graph neural network, we actually see a reduction in the accuracy. The third scenario is where we have the tau as a vector, but the amyloid, notice how all the values here are the same. So the amyloid is provided as a plus or minus, present or absent, as a binary input. In this scenario, you see here that the accuracy of the network in predicting actually goes up, and this is the highest accuracies we get. And so this provides us a nice framework where we use, well, instead of using the amyloid information in individual regions, we put a threshold and say, well, overall, is amyloid present or absent? And we put individual tau information in at a given time and predict the future tau for each individual subject. And these are some evaluation metrics, different, essentially different error measurements. And we see that with the tau plus amyloid positive or negative setting, we get the lowest errors. These are brain maps from the subjects where we essentially visualizing the errors in tau estimation. And so this is these are error maps. So we say this column showing error, and you can see that we tend to get some of the lowest errors in this tau plus amyloid positivity or negativity case. Another interesting thing that my grad student did for this project was to create an interpreter. So we wanted to understand, well, so what regions are most involved in taking this decision? And so we used this integrated gradients interpreter, which was developed by my student for this particular application. And the idea is to essentially aggregate the information starting from like a baseline value. We say, oh, let's assume the baseline tau is 0, 0, 0, and going from this state to the final state, we essentially accumulate gradients from the neural network to get the final value, which is the target tau as we know in a given state. And this actually helps us understand the contribution of different regions. And so I'm just going to jump to the final results slide. So what we saw with this method was that if we aggregate the contribution of some 10 selected ROIs that we know are very critical for early tau aggregation, we see that when we use this tau plus global amyloid beta, that's positivity or negativity status as an input, we get the highest contributions from the regions we know are sort of critical in early tau aggregation. These are some cyclic representations of node and edge importance, where you see that many of the regions that we know to be important for tau aggregation, they tend to show up in this representation. So in the interest of time, I'm going to quickly move to my third topic, and I'm going to go through it a little bit quicker because I'm supposed to wrap up by 10:30-ish in my time. So the next topic is Alzheimer's disease staging. And what our goal here is to create a model, a deep learning model that works very robustly to define how advanced Alzheimer's disease is in an individual. And so the idea behind it is a concept called contrastive learning, where the essential idea is to compare different versions of a vector. If you have an input, you compare different versions of that input and try to see how similar or different they are, so as to establish a self-supervised paradigm where you don't have training data. This is kind of like, it's not quite clustering in the traditional sense, but it achieves the same effect as clustering, where you don't have you don't have training labels to guide you. So the way we are achieving this is to go through this data augmentation step, where we create noisy instances of the same training, the initial input data that we provide. And then we try to, the contrastive learning paradigm tries to compare the data points with noisy versions of themselves and maximize the similarity between data points that are augmented versions of themselves versus data points that are different. And
excuse me, ma'am.
Yes?
I am interrupting you. Can you just put off the video and put it on? Because now it is totally blurred. We can't see anything.
Okay, let me try this again.
Yeah, please do that. Sorry for disturbing you.
Oh, no problem. Let me.
Yourself is also, your picture is also sometimes getting very blurred and sometimes it's coming the normal way.
Yeah, unfortunately, I'm not able to do much. I may have to, maybe I'll try to disconnect and reconnect. Would that work?
Yeah, it would be, I think the participants would bear that.
Okay, so I will try to disconnect. So one of the issues is, as I was saying, normally I connect from the Teams software, but I'm having some trouble today. So I use the desktop, the browser version, and so that is giving me less control. So let me try to end it and restart.
Okay, ma'am. Deepa ma'am, sorry to disturb you.
Yes, ma'am.
Yeah, next time when she comes in, Shoptoshi would let her in, and I think, yeah, then it would be better. What do you
Okay,
feel?
ma'am. Yeah, ma'am. Actually, in middle, once I said, but then I thought to wait and see if the net interconnectivity from our end is there. But I think it's not only because of the platform, maybe because of connectivity that
Yeah, it's due to
is the issue.
connectivity.
I think so.
Yeah, it's due to connectivity.
Let's wait, let her reconnect and let us see what
Yeah,
happens.
yeah. Participants, please bear with us. Sorry for the interruption. We can extend some few minutes if she actually gets a chance to come in and the presentation is better. Co-coordinator, sir, what do you feel? We can allow her some few minutes if she is available. Let's see.
Okay, it's okay, ma'am. But the thing is that already she had problem in connecting it in the at the beginning of the session.
Yeah.
So it may take some time her to join.
Yeah, that's what we are saying, that though the session is until 9 p.m. today, maybe we have to extend it for a few minutes as
Yes.
she is facing a problem to get
Uh,
connected.
yes, yes, yes.
And participants, I do think that you would bear with us.
She's trying to connect.
Yeah,
We
ma'am,
need,
you are audible now.
yes, ma'am, Dr. Jyota Datta is again back. I think she needs to get admitted.
Yeah, I have
Saptarshi
a,
needs to admit.
yeah,
Okay,
I have admitted her.
okay. I don't think she is there in the
No,
platform.
no, I too also
Yeah.
think the same.
Can you hear me now?
Yeah, we can hear you, but we can't see you.
Hold on, I'll try. So it was not letting me switch on my camera or mic. Can you see me now?
Yeah,
Yes,
we
ma'am.
can see you, but it is a blurred picture.
Oh, really? I actually changed. Now I'm like right next to my internet router. So
Yeah,
let me,
now it's better.
okay.
Better.
So I am, let me see.
Dr.
Right now,
Datta,
it's not giving me an option to share my screen though. It says that only meeting organizers and presenters can share.
ma'am, you are not being able to share your presentation.
Yeah, so I'm not being allowed to. So is there something you can allow from your end? Like it's
Yeah.
so
Just
it's
give us
saying
some.
screen share is not allowed. Oh, now now it's
Yes.
available. Okay, allow shared window.
Now you share the presentation and let us see what is the scenario.
Yeah, 1 second. Can you see my screen?
Ma'am, it is not yet visible, the presentation. Something is coming. Okay. Let's hold on a moment.
Do you see it now? Or?
Yes, we can see, but let's make it a little full screen from your end, ma'am. Then it's
How
in the
about now?
slide. Yeah. Yes, it is visible now. Much better
Okay,
and
great.
clearer.
Okay, great. That's a relief. Sorry about that. So as I was saying, we are trying to create this staging paradigm that is entirely deep learning based. Why is this important? Well, I talked about Brock staging earlier, so we can use some thresholding in different regions to define Brock stages, but there is enormous variability based on the data sources. And so what we were trying to create here is a robust model where you can train on one data set and then you apply to any data set with any data sort of not in a site specific or in a sort of scanner specific way. So this is something very generalizable, applying to all sites and all scanners. So once you train the model, you just directly apply and you stage. And so for this, we actually use data from 3 independent databases. And so a total of 2,000, over 2,600 data sets. One of our primary data sources is ADNI, or the Alzheimer's Disease Neuroimaging Initiative. We also have data from OASIS and HABS. So 3 independent databases. And so these are our staging results where when we apply the staging model, we have stage 0, 1, 2, 3, 4. So stage 0 is, you can think of that being there is no disease. Stage 1 is when disease starts developing, and stage 4 is where this is the highest levels of tau in the brain. And so these are the maps we get in from the the cortex and the subcortex from ADNI, OASIS, and HABS. Notice how HABS does not have any stage 4, and that is actually not unexpected, and because HABS is an aging study instead of Alzheimer's disease. So the HABS participants tend to have a very low proportion of people with full-on Alzheimer's disease. So there are, these are essentially people with earlier stages of cognitive impairment. So there are no stage 4s. And we look at the results based on different diagnostic groups. So we have ADNI here, which has a higher proportion of, so these, the stages are noted by colors here. So 0, 1, 2, 3, 4. So you can see here that HABS has only 0 through 3 here with in the amongst the cognitively normals, it's mostly stages 0 and 1 with like a smaller proportion of 2 and 3 in all of these cases. And then we look at MCI, which is mild cognitive impairment. So these are the diagnostic groups. And the third one is Alzheimer's disease. So you can see that some of these earlier stages are less represented as the disease category advances. So therefore, these stages, which are purely data driven, are actually related to what the ultimate diagnosis is for these subjects. We also look at the mean tau, and SUVR is a way to quantify the tau based on the PET image. And in the Brock ROIs, because Brock staging is a conventional way to stage, and so you see here for stages 0, 1, 2, 3, 4, these are the, for each of these Brock ROIs, which are listed here, you kind of see the evolution of tau based on the contrastive learning stages, which tells us a little bit more about how the tau accumulates. And then this is a map. So we're trying to look at something different. So out of our 900 plus subjects in ADNI, we identified about a small set of subjects that underwent conversion, which means they went from one disease state to the other. So 42 CNs, 76 MCI, and 41 AD subjects. So we use 159 observations, and these are all converters. So when we look at conversion and the corresponding stages, what it tells us is that roughly when we go from stage 1 to stage 2, that aligns with cognitive normalcy to mild cognitive impairment conversion. So that's like one diagnostic transition. And then MCI to AD roughly again aligns with stage 2 to stage 3 conversion, which is kind of like another way to look at disease progression in terms of in terms of the staging scheme. Another important result here is that when we look at correlations of how the stages advance versus versus the cognitive endpoint. So we have different things here. So many of these are cognitive endpoints. We also include age and ApoE, which is a genetic marker associated with amyloid, and then actual diagnosis. We see that for each of these, again, these graphs are a little bit detailed. The stars represent statistical significance, but what we see here is whether it's positive or negative correlation compared to Brock staging with contrastive clustering, there are tiny increases, or if it's negative correlation, then decreases, which essentially means we are getting better correlations with the cognitive markers. And this is important because keep in mind, our staging is purely data driven. We're only looking at imaging. We're not looking at any neuropsychological or cognitive markers. And that is telling us that this data driven staging tool is actually giving us metrics that are correlated with the cognitive performance in the individuals. And then this is my last slide on this topic, and then after that I'll move on to a slightly different direction. And so this is a map of cognitive decline risk based on tau stage. So you see, if you look at the probability of maintaining the same MMSE versus the MMSE. MMSE is actually a memory scoring technique. So it's a very important cognitive test in Alzheimer's disease. So you see how for stage 0, this kind of stays flat. For stages 2 and 3, that's where there is the maximum probability of maximum probability of change, and versus stage 4, which again here stays relatively flat. And this is the distribution of subjects in each of these groups. So now, as I said, I'm going to switch gears to the last topic of my talk today. So this is, again, so far we've been looking at imaging data. So we're going to take a very different approach and look at how people are sleeping and how that, can be a tool for detecting cognitive impairment early. And so the reason it's important to look at sleep is that chronic sleep disruptions have been linked to many diseases and are thought to be one of the earliest symptoms of Alzheimer's disease. It's also important because there are theories that, sleep might be a modifiable risk factor in AD, which means that if you change sleep habits, potentially there could be a therapeutic effect or a preventative effect. And again, these are areas under investigation. For now, our goal is to use sleep-based metrics that are that can be used to flag or identify at-risk individuals for further diagnosis, for cognitive evaluation, for recruitment to clinical trials for Alzheimer's disease, and so forth. So how is sleep monitored in a lab setting? The gold standard is polysomnography, or PSG, where a number of different, an individual is hooked up to a number of different sets of electrodes and other sensors that gives us a multitude of information. It's multimodal. We look at EEG, ECG, EOG, which is the eye movement, and EMG, which is muscle movement. And then there are also respiratory trackers and essentially covering brain activity, heart activity, muscle activity, how the eyes move around in the eye sockets, and then how the chest moves with respiration. So it's multimodal. The issue is that this is a very complicated setup. This is not something we can do at home on our own if we want to track our sleep, or if our doctors want to track our sleep routinely. And so this is one domain where wearable devices for monitoring sleep are becoming increasingly popular and useful. And so what we have developed is a transformer model for predicting cognitive performance and cognitive impairment from sleep. And so again, I don't want to go into too much of detail, but right now our model uses the whole night EEG, that's brain activity picked up by electrodes, and also sleep staging results, which are essentially looking at the EEG and the other PSG data sets epoch by epoch for each 30-second epoch, deciding whether this person is awake in REM sleep or in non-REM sleep. So we use two different databases for this analysis. One of them is MESA. This is essentially a database that was targeting heart disease, but then they also ran a parallel sleep study and a cognition study, and using two different cognitive tests, the DSCT and the CASI. The CASI is a little bit similar to the MMSE test that I was telling you about earlier. DSCT is a little bit more specific to coding of digit symbols. So for the MESA, this is what the PS, so imagine this is the top of the head, and these are locations of different sensors. And so these sensor positions are typically used to guide EEG sensor placement. And so in the case of MESA, we have sensors corresponding to some of these locations here, not everything, but FC, CZ, OZ, which is down here, and then C4 and M1. So for our analysis, we're using the C4 signal, and then M1 is our reference. We take the difference between the two. And then for the Mr. Oz, this is a male-only cohort, and then it's, again, the ultimate goal of that cohort is a little bit different. It's focused on osteoporosis, but again, this is an interesting large database where we have cognitive endpoints based on two different neuropsych tests, and we also have sleep data. So it's, again, a great resource for mining. So for each of these cohorts, the electrode placements can be a little bit different. So here we are using the C4 and the A1 as the reference. A1 is a little bit different from the M1. So this is our processing pipeline. And again, I don't want to go into too much detail, but the essential part is when you're working with these raw data sets, the data can be very noisy, and there may be some bad electrodes, or some. So essentially, it's important to remove some of the bad epochs and filter the data. So we have this protocol that my grad student developed to clean up the data. And some examples is that we have some of these checks in place to detect these bad epochs. And so where these gray bands are, these are the bad signal zones. And so in terms of the sleep stages, we actually put a different number corresponding to the stage to kind of indicate this is a bad epoch. And we also mask out the EG signal and set that to 0. So that's kind of like a processing detail, but it's a critical one. It was important in maintaining, in sort of ensuring we get strong numbers. And this is our transformer model. We compare it with handcrafted features based on an existing set of papers from our collaborator on this topic, who looked at, identified a lot of sleep features that are relevant to cognition. So we call these handcrafted features because these are predetermined sleep features based on some more traditional analytic ways to define them. And then we also looked at two different very well-established neural networks for sleep assessment. One is Tiny SleepNet, one is Dilated CNN. And again, these are confusion matrices that tell us, well, how well we are detecting unimpaired versus impaired subject based on each of the cognitive tests. So this is for CASI, one of the tests, and for the MESA cohort. And what a quick conclusion from these comparisons will be that, well, again, there's a lot of information here. You can focus on the accuracy numbers, whereas the other deep neural networks have about 67% accuracy. Handcrafted features give us about 56% accuracy. Our method with the transformer gives us about 72% accuracy, which is quite a bit of an increase compared to these other methods. And so this is the other test from MESA. So where the margin of accuracy with respect to some of the deep neural networks is a little smaller, but the handcrafted features have very low accuracy. This is another test from the Mr. Oz cohort, so where our accuracy is close to 79% compared to the other deep neural networks that have like 70 or 71%, handcrafted 59%. And then the last one, this is Trail B from MESA, where our accuracy is about 77.6, close to 78. The other deep neural networks, about 72. And handcrafted features about 55 or 56. So these are different. Again, the summary of this is that different methods, but we are able to get down to much more accurate numbers than other methods for detecting cognitive impairment from how a person is sleeping. Some of our ongoing work in this field focuses on wearables, because what I described is based on a sleep study that is based, using the full PSG setup with all of those sensors connected. So this is not something that's suitable for long-term assessment. So some recent work we've been doing in this field involves using Apple Watches for looking at the cardiac parameters and activity, and different types of headbands or portable EEG or wearable EEG devices to look at brain activity. So we still have studies underway to look at cognitive performance, but for now, I'm going to quickly show some results from a study that involves using these wearables and then staging sleep on them. And so our goal is to perform 4-class sleep staging with the Apple Watch data that I'll show now. So from the Apple Watch, we're getting instantaneous heart rate and activity, and this is based on collecting data for up to 7 nights from the subjects. We acquired data in our lab from 47 subjects, and some of these, this is the different sort of the race distribution. The cohort was more or less young. Average age was about 35. This is the network architecture. So there are many convolutional and LSTM type layers. LSTMs are usually used for time series analysis. And we also have these attention layers to dynamically extract features from these networks. Without going into too much detail, I'll say that there were 3 key elements to our network that we identified as being responsible for its higher accuracy. One is intra-epoch learning. So that means within each epoch of 30 seconds, we have 15 samples, and we're also deriving features within each epoch. We also rely on the sampling frequency, and what that means is when we get heart rate measures from devices such as the Apple Watch, and this is interesting. So when you use the Apple Watch for tracking your health, especially for looking at heart rate. What it does is it samples information irregularly. So when you're actually at rest, it's going to get, it assumes, well, you're not moving, so your heart rate is not quite variable. So you will get samples that are spaced far apart. So it's not going to spend its battery getting frequent measures of your heart rate. On the other hand, if you're exercising, your heart rate is changing quickly, it's higher and also fluctuating a lot. So it's going to, the watch is going to get more frequent measurements. Now that is not quite ideal for sleep tracking, because when you're asleep, your heart rate is usually lower, which means the Apple Watch is not going to sample it on its very frequently on its own. So what we did, two things. One is we got a custom app to get denser measurements, but at the same time, the other thing that we did was we from Apple, we, instead of just using this irregularly sampled time series, we also extract the sampling frequency. And in fact, it turns out the sampling frequency itself is informative for our sleep measures. And also from an architectural perspective, we incorporate what are called skip connections, where we use information that we extract from the early layers of the neural network and feed it directly. So we kind of bypass all these intermediate networks and feed it directly to the last layer. So these are kind of three key technical innovations here that are responsible for this network's highest performance. And we compare it with a wide series of, this is our method, SLAMS IFS, and we compare it with different other alternative networks. This method has the highest accuracies for sleep staging. These are confusion matrices. You see that there are 4 rows and 4 columns, because now we have like 4 stages we're looking at: wake, light sleep, deep sleep, and REM sleep. And this is predicted. The height-wise we have predicted, sideways we have observed or actual. And this, again, diagonal elements high. That's a good thing. That means you're accurate in detecting each class. And if off-diagonal elements are low, that means you have a smaller, making fewer errors. So again, this is our result, which is, you can see, quick visual check, highest diagonal terms, smaller off-diagonal terms. And we also looked at the contribution of to different traditional sleep measures used in the lab and how our method compares with other methods. And so this is EEG based metric. So this is kind of the gold standard, and this is our method, and these are the other ones. So the closest it is to the EEG result, the better. And so this is sleep efficiency, sleep onset latency, and then these are different ways to measure sleep time. So total, light, deep, REM, and these are fractions: light fraction, deep fraction, and REM fraction, like what fraction of the time you're asleep is spent in each of these types of sleep, light versus deep versus REM. So for majority of these cases, you see that these two dark blue bars are closest to each other compared to other methods. Not for everything, but for a majority of the cases, our method was a clear winner. And then this is what we call an ablation study in machine learning, where you take so when you're trying to test the contribution from different parts of a neural network, so you can take apart some components of the neural network and then run that study again. And that way you ultimately figure out what part of the network is actually contributing to the accuracy. And so, as I said, we have these 3 components: the I, the F, and the S. So intra epoch information, sampling frequency, and skip connections. And so this is a comparison of different components, like where you have IFS in there, FS, IS, IF, then only I, only F, only S. So we kind of pull apart the impacts of these components to show that, well, when we put all of them together, that is when we have maximum accuracy. We also experimentally applied this to 5-class sleep staging, where now instead of light sleep, we combine it. We split that epoch into this N1 phase, which is kind of like a transient sleep phase, and this is more stable light sleep. And the accuracies are clearly lower, but we are still, we are quite a bit better than the closest competitor in terms of all those methods I'd shown you earlier for 4-class sleep staging. The method that was closest in performance, we showed that our method outperforms that one. So with that, I'm going to wrap up today's talk. I'm sorry for all the internet issues that happened today. But yeah, I just wanted to take a moment to thank my lab members and my funding sources, and I would be happy to take questions at this time.
Thank you so much, Dr. Nata. Yes, the platform is now on for any kind of questions. This is a Q&A session. So participants, please go ahead with questions. All right, ma'am, we have a question from Dr. Shomodev. So let's see the question.
Yeah, I can see it. So will AI be
All
able
right.
to predict which patients with mild cognitive impairment will progress to Alzheimer's dementia? So the short answer is it really depends on the data and how well we can validate this, So there are a lot of AI models that people have tried to develop where they use, let's say, MR images, and we have actually one project in progress. The paper is still not submitted, but very close to submission, where we are looking at MRI imaging. And we're essentially trying to predict conversion. And the claim there is we are able to predict conversion up to 2 years ahead of it happening. So, but in my take on it is, in general, when you're talking about conversion, when you're talking about progressing from one disease state to the other, in most of these databases, the proportion of converters is relatively low. So whether it's my study or someone else's, it's important to be aware that these AI-based techniques for predicting conversion, even though some of the accuracies tend to be high, the training and the results are based on a relatively small number of data sets. And so I think we can be more confident of the tools as we accumulate more data. But for now, yes, there are methods, but most of those methods are validated based on relatively small data sets. Another question here, which imaging modalities, biomarkers, structural MRI, FDG PET, amyloid PET, tau PET do you find most informative early diagnosis for Alzheimer's progression? Does multimodal provide advantages? That's a great question. I think, so the current understanding and knowledge is that amyloid and tau are the measures that are the most sensitive for early AD. Again, if you're kind of looking at a variety of biomarkers, right now the most accessible, or in the near future, I think the most accessible biomarkers for people will be the plasma-based biomarkers or the blood biomarkers. Even though these are kind of work in progress, they're also, that space is expanding rapidly. So there are more reliable measures of amyloid and tau based on blood than we ever had before. So these are, many of them are validated against PET. That being said, PET imaging, I would personally consider PET imaging more reliable than the blood-based measures. Blood, as you can understand, is a global metric. So when you look at PET, you know which region has localized tau or not, especially for tau. That information, that spatial information really, really helps. In the early stage, other things like in the list, and I think that's a very thoughtfully curated list, structural MRI, FDG PET, these, especially atrophy measured from structural MRI and hypometabolism from FDG PET, these are very useful measures for downstream neurodegeneration. They tend to be a little less sensitive in the earliest stages. And so in those earliest stages, essentially the paradigm right now, even though it's not a perfect paradigm, the best metric that works right now is just to essentially say, well, is this subject or patient amyloid positive and tau positive? So we can apply some basic thresholds to say, well, above this is amyloid positive, above this is tau positive. And if it's imaging based, you can look at a few regions and say, I'm going to look at the aggregate amyloid from these regions because these are considered most sensitive. Same for tau. And then you apply a threshold to there and establish amyloid or tau positivity. For blood biomarkers, it's already global, so you apply some sort of threshold on the number and determine amyloid positive or tau positive. And so for most of the early cases, what people do is they try to see, well, is it amyloid positive? Is a person tau positive, or both? And currently the paradigm is if the person has both amyloid and tau positivity, that would qualify them as being classified as preclinical Alzheimer's patients rather than, normal individuals. So that's kind of the basic idea. So if you're really talking about early diagnosis, that is ultimately the main hard criterion that you're looking for. Multimodal analysis, as always, is important. And but that being said, there are challenges. So especially from an AI perspective, when you're working with multiple modalities, methodological complexity aside, one of the hard truths is that when you're looking for more modalities, then you're likely to have fewer data samples for training your model. This is what I can say, like, very frankly, as an AI person, that if you have two modalities, whatever data set you would have, the moment you jump to 3, your data size is going to reduce. You'll have certain people who will only have data from 2 modalities. You're going to have tons of missing data. So then there is this perpetual trade-off between total number of samples available versus, samples with full data from all modalities. So there is that challenge. But that being said, multimodality inherently has a big motivation in Alzheimer's analysis. And this is like, leave the AI side aside for once and kind of think about the disease in sort of strict, from clinical terms. So I talked about the ATN framework, amyloid tau neurodegeneration, and that's like a great way to capture the complexity in Alzheimer's disease, but it's not the most complete framework. There are many things that are poorly understood. And again, ATN is considered a biomarker framework. So you get amyloid tau neurodegeneration biomarkers and you characterize the disease in ways that are just beyond simple, cognitive measures. And in a lot of ways, Alzheimer's research based on the ATN system is way more advanced than some of the other dementias. For instance, in frontotemporal dementia and other dementia I work with, there are no such established standardized biomarker framework. So ATN is still better than not having a biomarker framework. But the multimodal piece, I want to comment on that. There are things like, for instance, inflammation. There are synaptic density and other synaptic effects that could potentially be captured with PET or other imaging or non-imaging based methods. So these are things that are not quite built into a standard framework yet, but they are known to have a lot of mechanistic roles in disease progression. So it is known for a fact that you have high levels of inflammation that is associated with multiple diseases, not just Alzheimer's disease. But then inflammation is also one of those very tricky things where many conditions trigger inflammation. It is you can think of it, those biomarkers, being sensitive but not specific. So again, this is not specific to Alzheimer's disease. It's for studying different conditions, but it's really important to look beyond ATNN, look at other biomarkers, and essentially that the key to that lies in multimodal analysis.
Any more questions, please?
There is another question. Given the complementary structural information from MRI and PET and temporal dynamics in EEG, is it feasible for multimodal fusion methods such as contrastive self-supervised alignment, cross-modal transformers, graph-based integration of EEG connectivity? Yeah, those are actually great questions. People have tried to use, I've not worked a lot with just pure EEG. Like, again, I work with sleep EEG. I've not worked with awake EEG. That's kind of like, I think that's what you're trying to hint at for the functional dynamics. And so you could give people tasks, look at how they're performing. And the graph-based EEG techniques, especially when you look at EEG connectivity, you would require high density measurements. I'm not aware of large public data sets that have EEG and fMRI and or PET, but there have been a number of more sort of smaller cohorts where these data samples have been collected in individuals. There are also cases where people tried to do fMRI and EEG simultaneously, and those have yielded rich information. There have also been studies where they tried to do fMRI and PET together. I'm not sure if it's specifically, if any of those have been done for Alzheimer's disease, but for some of these other, looking at dopaminergic receptors, or where you do displacement studies with the PET, and you can in parallel look at the bold signal from the functional MRI. And many of these studies give mechanistic information. To my knowledge, most of these are sort of more traditional investigations, non-AI based, because the more of these data types that you add, again, as I was saying before, your data size, your ability to collect create a large database typically reduces, because it could also be expensive to acquire these data sets. So no, I'm not aware of a lot of cross-modal studies that integrate EEG, MRI, and PET in the context of Alzheimer's disease using different AI techniques. But there are more traditional methods that have certainly been applied, published, and many of them in high-profile journals, integrating EEG and different variants of MRI with PET. I see another question here. Can AI personalize treatment plans for individual AD patients? So that's, again, maybe down the line. Right now, what do we have in terms of treatment plans? And that's kind of the big question here, because there are a couple of drugs that have been approved by the FDA for Alzheimer's disease, but there are different opinions surrounding how effective these drugs are, and for some fraction of for patients who have been administered these drugs, there have been some deleterious side effects. So the treatment frameworks for Alzheimer's are yet to be fully developed. So we don't have good, reliable treatments. We have only a few drugs that are out there, others under discovery, sort of under investigation, and so forth. So I think using AI to personalize treatment plans, it's something I think it's on people's wish lists. I think it's a wish list item still, but it's going to take some time, because we first need some effective treatment plans out there before we can get to the point where, well, we can mine large data sets, look at clinical history, look at EHR data, and then try to see, well, what treatment works for whom, and so forth. I see another question here. Any publicly available data set, MR PET scans apart from OASIS? So I think the best, so ADNI, OASIS are great data sets. The other data set to look at is the NACC. I don't know if NACC has any overlap with ADNI or OASIS, but the NACC is essentially the it's kind of aggregate of all data from the ADRCs, which are the Alzheimer's Disease Research Centers all across the US, funded by the National Institute on Aging. So the NACC would be a good site to kind of look at aggregate data sets from different modalities. Research prospect of data science or computer science in this field and other medical domains suggest research ideas. Well, again, it depends on what what specific sub area of this field you're interested in developing. I mean, some of the things that we're doing, I already talked about. Outside of that, there are different people doing different things. For instance, there's been a lot of interesting work that uses AI towards molecular discovery and understanding molecular structures. There's been a lot of interesting advances, for instance, on protein folding, leading to a recent Nobel Prize in that field. So sort of this molecular discovery, if I kind of try to generalize a little bit, this is one of those directions where I think a lot of advancement is still yet to happen, because these tools can be used not only to further our understanding of different conditions, but also can be leveraged for drug discovery. And so there are many sort of research directions in progress aiming at building new drug candidates by compiling large libraries of molecular structures and so forth. So again, that chemistry side of things in terms of just drug discovery, that's another sort of large domain of AI-based research, not just for Alzheimer's disease, but also other disease conditions. And again, that's outside of my current range of topics. The other thing that I didn't touch upon is I think that I would allude to one of the previous questions about personalizing treatment plans. There are people who are working, for instance, with looking at medical history, looking at the EMR, EHR, the medical records of individuals, and seeing, well, if we comb through the EHR data using different language models, like large language models, what can we get out of that? Can we flag individuals for specific diseases and so forth? And again, not specific to Alzheimer's disease, but you could essentially use NLP, natural language processing, with large language models, comb through the data and try to flag individuals. These are, I mean, some things I can think of beyond the range of things that we're doing right now. Although I didn't cover it in this current talk, we're doing a lot of work with the genetics data, because again, for late onset AD, so again, there are broadly kind of two types of Alzheimer's disease, and it's also true for some other dementia types, where there are some genetically sort of some genetic versions of the diseases. These are the familial diseases. You have Alzheimer's disease in these cases because of certain genes that you've inherited. And the more preponderant form of Alzheimer's disease, the more prevalent form of Alzheimer's disease is called late onset Alzheimer's disease. These are the non-familial variants. These are the sporadic variants. So even in these, you have some genetic contributions. For instance, if you have the ApoE E4 allele, then that makes it more probable that you'll have Alzheimer's disease. However, it's not deterministic. It's not an if-or condition. You're more likely, but that doesn't mean you will actually get it. But there is value to investigating genetics of subjects, and using AI to go beyond GWAS studies that are largely based on linear models. And so that's another domain where you could look at Alzheimer's genetics, or you could look at data from modalities that are understudied so far in the AD field. So yeah, just some rough thoughts.
All right, thank you so much, ma'am. I have just one question, and probably this will be the last for the time crunch and all. So, like this particular disease, I mean, Alzheimer's disease, it's genetic. It seems to be. So, like it is like paternal gene carrier or the maternal carrier. I mean, as per the studies.
It's not genetic in that traditional sense. That's what I was saying. So there are a small fraction of Alzheimer's patients have familial AD. So I do not believe it's either maternal or paternal. These are not related to the X or Y chromosomes. So the ApoE, the familial cases, they have two different genes, the APP and presenilin 1 or 2. I forget which ones. I don't work with familial AD data much, but so those are certain genes are implicated for the familial cases. But the largest fraction of Alzheimer's patients right now are these sporadic Alzheimer's patients. So these are the late. It's called. The terminologies used are familial, often called early onset AD. These are patients that have certain genes. They are definitely going to get it, except it's sometimes, again, a small portion are expected to get it, don't get it, then they're selected for investigations. That's how one of the very interesting protective genes for AD was discovered. And there was some very interesting work based on like this person from Colombia, I believe, who was very, very, very likely to get the disease because he had all the implicated genes, and then they didn't get it. That helped them so this person was genotyped, and that's when they discovered, well, there is a protective gene that this person has. And so there is a lot of interesting research that goes on that front by kind of studying these families that have history of a disease, but that's not the vast majority. The vast majority are these sporadic cases where they get the disease, They may or may not have that ApoE4 allele, which is by far the most, I think, the most well-known, the well-known genetic factor, risk factor for Alzheimer's disease. But again, there is no guarantee, even if you have ApoE epsilon 4, there is no guarantee you'll actually get the disease. And so it is, in that sense, yes, there is a genetic side to it. So having a certain set of genes alleles may predispose you and enhance your risk for Alzheimer's disease, but there is no guarantee. There's no way to say you definitively that you will get the disease. Does that help?
All right. That's great, ma'am. So it's still under research and but it was really informative, very much. So with this, we come to the end of the session. So on behalf of the organizing committee of Future Institute of Engineering and Management, and on my own behalf, it is my privilege to deliver the vote of thanks for today's session. First and foremost, I would like to extend our heartfelt gratitude to Dr. Joyita Datta for taking the time to join us and deliver such an insightful talk on Alzheimer's diseases and its pre-symptoms, neurological factors associated with it, various PET imaging for AD. Your explanations, ma'am, of how Alzheimer's disease is the most common cause of dementia, its evolution using AI techniques, diffusion probabilistic model, prediction model, various evaluation matrices, tau progression, various progression stages, how sleep disturbances is related to AD, sleep monitoring, and many others were both thought-provoking and highly relevant to our faculty's developmental goals. So I would also like to acknowledge our organizing team for the meticulous planning and seamless coordination. Thank you so much, ma'am.
Well, I just wanted to also share a few comments. Like, I really appreciate the opportunity to talk to everyone today. I apologize for all the internet issues. I hope you could still hear most of the talk. And I wanted to thank Dr. Bhattacharya for not just inviting me, but also kind of guiding me through the steps and, dealing with all the crazy logistics of making this happen. So thank you all for this opportunity. It was an absolute pleasure to talk today.
Thank you so much, ma'am.
Thank you. Bye-bye.
Bye.